Hello students, welcome to Engineers Academy. Do hit the subscribe button if you haven't subscribed my channel yet. Now we are going to solve this problem which says that determine the normal force, shear force and bending moment acting at point B of the two-member frame shown in figure 7.6a. So we are required to find the normal force, shear force and bending moment at this particular point B of the member AC. So before going to solve this problem, we need to find the support reactions at A and D. But if we determine the reactions at A and the support reaction at C, since we are going to find the internal forces at B, so that will be sufficient. There is no need to find the reactions at D. So we will find the force applied by this DC member on this AC, and we will find the reactions at this pin support at A. So at pin support we will have two reactions. We will have AX reaction like this. Let's say at A we have AX reaction and we have AY reaction. So we need to find this AX and AY, and this DC member of the frame is going to apply the force on this BC member in the upward direction like this. So this will be the force applied by DC member. So this is FDC, and as a reaction this AC member will apply the same force on this DC member but in the opposite direction. So that will be FDC. So both will have same magnitude but opposite direction. So this DC member will have that same force here at joint D as well, since if this AC member is applying the force on DC member in this direction, so we will have that same FDC in this direction as well, and this DC member is in compression. So now then the next task is to find the resultant of this distributed load. So the resultant of this rectangular distributed load will be equal to the area of this rectangular distributed load, and that force, that resultant force will be acting at the geometric center of this rectangular area. So the geometric center of this rectangular area will be at its midpoint, which will be at a distance of 4 feet. So the length of this rectangular area is 8. So the resultant will be acting at its midpoint, and that midpoint is at a distance of 4 feet. And the resultant which will represent the resultant concentrated load, which will represent this rectangular distributed load, will be equal to the area of this rectangle. So the area of this rectangle is this 50 pound-feet multiplied by 8 feet. So this is the height, or we can say that the width multiplied by length. So 50 into 8 will give us 400 pounds. So we have that 400 pounds here, and this 400 pound, the line of action of this 400 pound force will pass through the geometric center of this rectangle, and that geometric center is obviously it must be at a distance of 4 feet from both the ends. So now we have converted this distributed load into its resultant, and we have represented it X, A, Y and that FDC force. Now we are going to find the reaction forces. So I will say that first find the reactions. So for finding the reactions, we can apply the moment about point C equals to 0. Since this member AC, the whole frame is in equilibrium, so we can say that the summation of moment about point C, that it must be equals to 0, and the counterclockwise moment is assumed to be positive. So now as we can see that this AX is passing through that point C, so it's not going to produce the moment about point C, since its moment arm from that point C is 0, and this DC is passing through this point C, so it's not going to produce the moment about that point C. So only this AY and this 400 pound force is applying the moment about point C. So this AY is producing the clockwise moment about point C, so we will write minus, and AY and the moment arm of this AY from that point C is the length of this member AC. So we will multiply this AY with 8. So that is 8 AY. So 8 feet is the moment arm of this AY support reaction. Similarly, this 400 pound force is producing the counterclockwise moment about point C. So we will write plus 400, and the moment arm of this 400 pound force is this 4 feet, the perpendicular distance of 4 feet. So we will multiply this with 4, and this is equal to 0. So now we can write that minus 8 AY is equal to minus 400 into 4, divide both sides by minus 8. So minus will cancel out, and AY will be equal to, so this will be 400 divided by 2, so this is 200 pounds. So AY support reaction is 200 pounds. Similarly, if we apply the summation of forces along X, that must be equals to 0. Towards the right is our positive horizontal direction. Now to find the summation of forces along X, we have to resolve this FDC into its components, and we are given this dimension, the length of this AC member, and the distance between point A and D, 6 feet. So if this DC member is making some angle theta here, let's say, let me represent that angle. Let's say that we have some angle theta here, and here we have that FDC. So we can resolve this FDC into its components. We will have two components of this FDC. So we will have one component like this, and we will have one component like this. So if this is the angle theta, then this component will be FDC cos of theta, and this one will be FDC sine of theta. Now the information of this theta is given in terms of these dimensions, as I have already told you people. So that the length of AC is 8 feet, and this is the distance between A and D is 6 feet. So we can find cos of theta and sine of theta using these dimensions. But you people will wonder that why here we have this 5, 4 and 3. So that we can see that if we consider this small triangle like this, so then this length is 4. So this is the midpoint. So again, this will be 3, and the hypotenuse will be 5. So they are considering this small triangle like this, but we can consider these whole dimensions. So if I find cos of theta from this right angle triangle, the last triangle, we can say that cos of theta will be the base of this right angle triangle. So the base is this 8 feet. So 8 divided by hypotenuse. So this is the hypotenuse, which is the length of DC member, which is not known. So we have to find this DC length. So we can always apply the Pythagoras theorem for a right angle triangle. So DC square is equal to this square plus this square. So we can say that this is 6 square plus 8 square, and if we take the square root on both sides of the equation, so we will get DC length, and which is 6 square is 36 and 8 square is 64, so we get 10. So DC, the member of the member DC length is 10 feet. So now we can say that cos of theta is 8 divided by 10, and similarly sine of theta will be the perpendicular. So the perpendicular is this 6 feet by hypotenuse. So we can say that this is 6 divided by DC length, which is 10. So this is cos of theta and this is sine of theta. Now if we apply the summation of forces along X, so we will have two components here. So the summation of forces along x will be this ax. X is in the negative x, so I will write minus ax, and this cos component of FDC, so we will write plus FDC cos of theta, and cos of theta is 8 divided by 10. So I will multiply this with 8 divided by 10, and this is equal to 0. So now we have one equation and two unknowns. The x is unknown and FDC is unknown. Similarly, if we apply the summation of forces along y, that must be equals to 0. In the upward direction is our positive y direction. So again we have this ay. This ay is in the positive direction, so we will write plus ay minus 400 and plus this component, which is the sine component. So we can write that plus ay minus 400 and plus FDC sine of theta. Sine of theta is 6 divided by 10. This is equal to 0. Now again we have another equation in which we have two unknowns, and now as a whole we have two equations, but we have three unknowns: ax, ay, and FDC. So this will not give us the solution, so we have to apply another equilibrium condition, and we have to apply the summation of moment about point A equals to 0. The counterclockwise moment is assumed to be positive. So now we can see that this is FDC 8 divided by 10. This is the cos component, and this one is FDC 6 divided by 10. This is the sine component. So now we have to apply the summation of moment about point A. So the support reactions at A, they will not come into our equation, since they are not going to produce the moment about point A. This FDC cos component is passing through that point A as well, so it's not going to produce the moment about point A. So only this component and this component, they are producing the moment about point A. So this FDC 6 divided by 10, which is the sine component, is going to produce the moment about point A in the counterclockwise direction. So I will write plus FDC 6 divided by 10. The moment arm of this component from that point A is the length of this AC, so we will multiply it with 8. And similarly, this 400 pound force is producing the clockwise moment about point A, so we will write minus 400, and the perpendicular distance of this 400 pound force from that point A is 4 feet, so we will multiply this with 4, and this is equal to 0. And from this we can write that FDC 6 divided by 10 into 8 is equal to 400 into 4. And if we cross multiply, so we will have 10 divided by 6 into 8. So this will give us FDC. So let's find FDC. So FDC is 400 multiplied by 4 multiplied by 10 divided by 6 into 8. So this is 333.33. Let me write it. FDC is 1000 divided by 3 pounds, or we can say that FDC is 333.33 pounds. Now we have determined FDC. We can plug in that FDC value in both of these equations, so that both of these equations will give us AX and AY respectively. So let's put these, this is equation 1 and this is equation 2. So let's put FDC value in equation 1. So we will have AX from equation 1, we will have AX equal to FDC 8 divided by 10, and we have FDC, let me write it in fractions. So FDC is 1000 divided by 3 into 8 divided by 10, so which is my answer multiplied by 8 divided by 10. So this gives me AX equals to 800 divided by 3 pounds or 266.67 pounds. Similarly, if we plug in this DC value in equation number 2, so we will get AY from this equation number 2. So now AY minus 400 plus FDC, which is 1000 divided by 3 into 6 divided by 10 equals to 0. So minus 400 plus 1000 divided by 3 multiplied by 6 divided by 10. So this gives us minus 200. So AY minus 200 equals to 0, or we can say that AY equals to 200 pounds. So now we have determined this AX, AY. So let me represent all those. So now this is our free body diagram of that AC member, and now we have the AX value. The AX value is 266.67 pounds. The AY value is 200 pounds, and FDC value is 333.33 pounds. Now in order to find the normal force, shear force and bending moment at this point B, at the midpoint of this AC member, we have to cut out a section. We have to consider a segment, since the normal force, shear force and bending moment are the internal forces. So we have to cut this AC member into two segments. Let's say this is our point B. So we have to cut out a segment AB. So let's cut this. So now this is our AB segment, and now when we cut this segment, we have that distributed load from A to B in a like this, in a rectangular shape. So we have to show that we have to cut out this AC member with the distributed load, not with the resultant load. Since when we cut that segment, we cut out that rectangular distributed load into two segments as well. So we have to consider the distributed loads before making a segment of a particular beam or a member. So we have that distributed load from A to B in a shape of rectangle, and the height of this distributed load is 50 pound-feet. So this is my 50 pound/feet distributed load, and now the length of this rectangular area is 4 feet, since that point B is at the midpoint of AC member. So now again we have to draw another free body diagram, and first of all we have to write the resultant of this rectangular distributed load. It's the resultant concentrated load, and that resultant concentrated load value will be equal to the area of this particular rectangle, and the area of this particular rectangle will be equal to the height multiplied by this length. So this is 50 multiplied by 4. So now 50 multiplied by 4 is 200. So we will write 200 pounds. So now we have represented that distributed load by its corresponding concentrated resultant. And now we have to represent the internal forces. So at B we will have the normal force, and B we have to show the shear force. So the positive convention for the shear force on the right hand side of the segment is in the downward direction. So this will be my VB, the shear force at point B, and then we have to represent the bending moment at B. So again we have to draw according to the positive convention, and the positive convention on the right hand side of the segment for bending moment is in the counterclockwise direction. So this is our positive convention for the bending moment on the right hand side of any segment. So this is my moment about point B, that is the bending moment at point B. So this is when we are considering the AB segment. This is our AB segment. We can consider BC segment as well for our calculation, and we will get the same results for NB, the normal force, the shear force, and the bending moment. So now let me write the AX value. This AY is 200 pounds. Now we are considering segment AB for our calculation, and I will suggest you people to just draw the free body diagram of this BC segment and represent all the internal forces, that is normal force, shear force, and bending moment, and find the solution, find the values of NB, VB, and MB, and then let me know in the comments that if your answers are the same as of I have considered this AB segment. So now while considering AB segment, again we are going to apply the equilibrium condition since the whole frame is in equilibrium. So again we are going to apply the summation of forces along X, that must be equals to 0 while considering segment AB. So now we have this AX and we have this NB. Towards the right is our positive direction always. So this is my positive direction. We have plus NB minus AX equals to 0, and B AX is 266.67 equals to 0, and B is equal to 266.67 pounds. So this is the normal force at point B. Similarly, the summation of forces along Y, that must be equals to 0 as well. This is our positive Y direction in the upward direction. Now we have AY in the upward direction, so plus AY minus 200 minus VB. So we will write plus 200 minus 200 minus VB equals to 0, and from this we get VB, the shear force at point B, is equal to 0. And similarly, if we apply the summation of moment about point A equals to 0, the counterclockwise moment is assumed to be positive. Now AX and AY, they are not going to produce the moment about point A since they are passing through this point A. So this 200 pound force is producing the clockwise moment, and its perpendicular distance, the moment arm of this 200 force from that point A is this distance, which is the half of 4 feet. So that is 2 feet. So we will write minus 200 into 2. Then VB is also producing the clockwise moment, so we will write minus VB is 0. So, and the perpendicular distance of this VB from that point A is 4 feet. So 0 into 4 will be 0. And then we have to add up this bending moment. Since it's a couple, it's a free vector, so we will add it, and it's a counterclockwise moment, so we will write plus MB, and this is equal to 0. And B is passing to that point A, so it's not going to produce the moment about point A since its moment arm from point A is 0. So now we can say that this is minus 400 plus MB equals to 0. MB is equal to 400 pound feet. This is 200 in pounds and 2 is in feet, so the units will be pound feet for MB. And the direction is counterclockwise. So now the normal force at point B is 266.67 pounds. The shear force at point B is 0, and the bending moment at point B is 400 pound feet. So I will recommend you people to use this BC member and find these answers, and let me know in the comments if your answers and my answer coincide with each other. So I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from chapter 7, Hibbeler Statics.